Hello everyone, today I will be presenting my work on Fourier prior-based two-stage architecture for image restoration. There are several instances where images get degraded by environmental factors such as haze, rain, lighting conditions, and noise, which significantly degrades the performance of computer vision tasks. Therefore, image restoration is a critical pre-processing task. Over the years, there are several deep learning architectures proposed that can directly learn from the data presented, which improved the adaptability of the models to newer scenarios of non-homogeneous distributions of degradation. Although several encoder-decoder based architectures have been proposed over the years, there are several limitations of these models, such as limited receptive fields for convolution layers, can't capture long-range dependencies within an image. To overcome this, self-attention and transformers were used, but their computational complexity increases quadratically with increase in input dimension. Also, these models tend to overfit as they neglect the physical properties of the degradations. We analyzed the degraded images in frequency domain and observed that if we reconstruct the image by amplitude spectrum of the clean image and phase spectrum of the degraded image, the generated image are significant, the degradations in the generated image are significantly suppressed. Therefore, we take this as a prior that amplitude spectrum is affected by the degradation while phase retains the intricate details within an image. So we propose a two-stage architecture wherein the first stage is amplitude refinement and the second stage is phase refinement. Given a degraded image, amplitude refinement unit refines the amplitude spectrum and we reconstruct the feature map by taking the amplitude spectrum from the generated image, from the generated feature map and phase directly from the degraded image. In order to ensure learning of amplitude spectrum in stage 1, we use L1 loss function between the amplitude spectrums obtained between the intermediate feature map or output and ground truth. Whereas in the second stage, we refine the phase spectrum and use loss functions as L1 loss between the output and ground truth, SSIM loss, frequency domain loss. These are the architectures of amplitude refinement unit and phase refinement unit. In ARU, we use multi-scale inputs for learning. The main feature extractor is Fourier amplitude recovery unit, which is a CNN transformer based network. It has three different branches. The first CNN branch extracts local feature. The second is a transformer branch, which extracts global features from the amplitude spectrum. And the third is a residual branch. All feature maps from different scales are fused by the feature extraction block and fusion blocks. The PRU or the phase refinement unit is a simple network with series of feature extractor blocks. We evaluated the architecture for image deraining, dehazing, and low light enhancement across both synthetic and real world datasets. Across all datasets, we got improvements in PSNR and SSIM values. The computational complexity of the architecture is lower as compared to transformer based architectures. However, in some cases, it is higher than CNNs. These are some qualitative results. We further conducted several ablation studies, which included first the efficacy of Fourier prior, wherein we train one network, the first network, as a one-stage network. A second network, we replace the positions of ARU and PRU, and the third is our proposed network. In second study, we evaluated the model with and without the multi-scale inputs. And in the third study, we tried different combinations of loss functions. The combination of intermediate loss for stage 1, along with spatial domain, frequency domain, and SSIM loss in the second stage gave us the best results. These are the references. Thank you.